So what we're going to do now is we're going to take a look at how do we use integrals in the integration of power series in order to find function representations of power series. Okay, so one of the cool things that we can do with a power series is that we can actually take the integral of each individual term, okay, and then that will, and by taking the integral of each individual term, that actually implies that we could take the integral of the entirety of the function representation of the power series. And I'll show you what I mean by that by actually giving you an example. So let's take a look at this. Let's say we have negative x cubed minus x to the fourth over 2, minus x to the fifth over 3, minus x to the sixth over 4, minus x to the seventh over 5, minus x to the eighth over 6, etc., etc. Okay? And some things that we're going to need to know is we're going to need to know that, one, the sum of x to the n is going to equal 1 over 1 minus x. Okay? And so that's actually going to come in very important inside of this, this particular problem. It's very common. We use it a lot inside of finding functions for power series. Okay? And so we're going to utilize this a little bit later on as well. All right? And then the second thing that I'm going to need to know, or that I'm going to need to notice, and this is just a little foreshadowing, is that I've got d dx of x to the n plus 1 over n plus 1. So the derivative of that is going to equal x to the n. Okay? Or, conversely, the integral of x to the n is going to equal x to the n plus 1 over n plus 1. Right? Okay, and that's just standard working with powers. Yes? I mean, that's the power rule for integration. All right, so now let's utilize this in order to kind of find this function representation for the power series. So one of the things that I want to do here with this particular series is I want to pull out any terms that are not going to be dependent upon n. Any like terms. Okay? And so I'm going to pull out an x squared term. Okay? I'll pull out an x cubed term. And so this is going to give me negative x cubed, times 1 plus x over 2 plus x squared over 3 plus x cubed over 4 plus x to the fourth over 5 plus x to the fifth over 6 plus ... Okay? All right, cool. So that's good. And what that's going to allow me to do is that's going to allow me, I'm going to end up being able to pull out a negative x cubed if that's what I want out of the entire summation, because the cubed is not going to be dependent upon n. Okay, so there's no n inside of negative x cubed, so I can actually pull it out of the summation if I want to and just multiply the whole thing by it. Now, here's the thing though. One thing that I want to notice is that when I write this, okay, I'm going to get negative x cubed times, and then I'm going to write this as a summation. Okay, it's going to be times, and we'll say it's the sum, okay, n equals 0 up to infinity, okay, of negative x cubed. And then this is going to end up being x to the n over n plus 1, right? Because 1 is going to be 0 plus 1, 2 is 1 plus 1, 3 is 2 plus 1, 4 is 3 plus 1, etc., etc. Okay? Which is great, but it's not exactly this yet. Okay? And the reason why I wanted to get it to this term, or that x to the n plus 1 over n plus 1, is because then I'm going to actually be able to go in and integrate each one of the terms, okay? And then that's actually going to allow me to then say that my final result is the integration of this 1 over 1 minus x. All right? So what I'm going to do is I'm going to actually add a plus 1. So this is now going to equal the sum, n equals 0 up to infinity, of negative x squared times x to the n plus 1 over n plus 1. So now, by adding in that plus 1, I've now got this particular value, the x to the n plus 1 over n plus 1, which is great. That's exactly what I want, okay? So now, what that's going to be then is that's going to then equal negative x squared times the sum, n equals 0 up to infinity, of x to the n plus 1 over n plus 1. All right? Now, each one of these terms, right? Each one of the x to the n plus 1 over n plus 1 terms is the integral of x to the n. And the summation for x to the n is 1 over 1 minus x. Okay? So what I can do here is I can kind of say something along those lines. Is I can say, okay, well, this is then going to equal negative x squared times the sum of n equals 0 up to infinity of the integral of x to the n dx. Okay? Right? Because that's what that thing is. That's the integral there. And what I'm going to then do then is I'm going to make this negative x squared times the integral of the sum n equals 0 up to infinity of x to the n, and then the whole thing dx. And this is then negative x squared, and so this summation, n equals 0 up to infinity of x to the n, is 1 over 1 minus x. But we're now going to be taking that integral of 1 over 1 minus x. And there we go. Okay? Take that integral. So we'll utilize u substitution. So we're going to let u equal 1 minus x and du equal to now negative dx. So negative du is equal to dx. So then my integral of 1 over 1 minus x is going to equal the integral of negative 1 over u du, which equals the natural log, the negative natural log of u, okay, which equals the negative natural log of 1 minus x in absolute value. And so consequently what we get now is we get negative x squared times negative natural log of 1 minus x, which is then just equal to x squared natural log of 1 minus x. And that is the representation of our function. So what I wanted to demonstrate here is how do we utilize integration in order to find function representations of power series. And so what we'll do with that, or how we'll go about doing that, is we're going to first come in and we're going to say, okay, well, first I'm going to adapt this so that I either end up with the integral of a, so I'm going to end up with an integral of a power series that I know. In this case, the sum of x to the n, which equals 1 over 1 minus x. Okay? So I do that, and then what I'm going to do now is I'm going to manipulate my series to where I end up with that x to the n plus 1 over n plus 1, right? That gives me the integral of our known series, all right? You can see actually here that we can pull out the term negative x squared, okay? And what I'll then get now, okay, is I'll get negative x squared times the sum of the integral of my known series, all right? And then that will be then negative x squared times the integral of 1 over 1 minus x now, okay? Now instead of integrating each term of x to the n, I can now just integrate 1 over 1 minus x. And so what I end up with now is I end up with that term that I pulled out, the negative x squared times negative natural log of 1 minus x, or my integral, okay? And we can do this each and every time. If we can actually do that with, in this case with, the power rule for integration, right? That's going to end up becoming really handy. We're going to actually see one in just a little bit for differentiation as well. Okay, so that completes this example and that discussion on the integrals for power series.